In this demonstration, we will practically explore both the CLT, central limit theorem, and empirical, that is 68, 95, 99.7% rule, using real data from Framingham heart study. For simplicity, we'll use the diastolic blood pressure values from the heart dataset and perform our analysis in Excel. So let's get started. First, select the entire column containing the diastolic blood pressure. Control C to copy all these values. Then this plus button to open up a new sheet, and then Control V to paste all these values in column A of this new sheet. Okay, so we have 5,209 values from Framingham heart study. But for this exercise, let's imagine that these represent the entire population. For example, all individuals in a large city who received the Pfizer COVID-19 vaccine. In reality, it is impractical to measure the blood pressure of every single individual in such a large population. Instead, we select a smaller sample. Let's say we take a group of 100 individuals at a time. And by repeatedly taking these samples, we will be able to demonstrate two things. First, we will observe the central limit theorem in action, showing that how sample averages approximate a normal distribution. And secondly, we'll confirm if the empirical rule, 68, 95, 99.7% rule, accurately predicts how these averages distribute across the true population mean. In this demonstration, we will first measure the so-called unknown population mean of diastolic blood pressure. We will later verify how accurately we can estimate this mean by using 95% confidence interval rule. Then we will take 1,000 samples, each sample consisting of 100 randomly selected individuals from our so-called population. And then we will demonstrate the central limit theorem, which states that the distribution of sample means from a large number of independent, identically distributed samples approaches a normal distribution regardless of the original population distribution. Calculate the so-called unknown population mean. And just enter, let's label it unknown population mean, and the formula is simple average parentheses A colon A, and it comes down to be 85.36 millimeters of mercury. Next, let's take 1,000 sample, and each sample would be consisting of 100 randomly selected individuals from our quote-unquote population. Okay, let's leave the column C as blank. We'll start from column D, and let's name this column as participant 1, okay, P1, okay, and then I'm gonna drag this horizontally until I have 100 participants labeled. Okay, I'm looking at the prompt here. So 100 comes all the way to column CY. Okay. Now I can just randomly select any of the participants from here, but a very a useful formula is here. Just write it down or remember it, whatever. I created this using ChatGPT. Equals index parentheses $A colon $A comma rand or random between parentheses 2 to 5,209 parentheses closed parentheses closed. So it has just randomly selected any of the values from our so-called population. Okay, and if I drag it horizontally, grabbing the fill handle, it will just select 100 participants from our population. Okay, so let's do it. Okay, I'm gonna drag it all the way to CY. So now we see that Excel has, using that formula, picked up one first person randomly from here, who had the diastolic blood pressure of 80, second who has a diastolic blood pressure of 76, and so on. Okay, I'm gonna narrow all these columns down so it is easier for me to manage and see. Okay, so now we have all these we have our first sample created, right? And I'm going to create 1,000 samples of these 100 individuals each. Okay, so I'm going to just drag it down all the way to 1,001th column. As you see, as we scroll down, 300, 400, 500, 600, the 800s, and we are close to 1,000. And okay, 1,001, because one, the column, the row one was headers. Okay, so now we have created 1,000 samples of 100 individuals just randomly selected, right? Now let's demonstrate a central limit theorem. We are gonna see if the distribution of the sample means, and we already know that we have a large number of independent, identically distributed samples. We'll see if the distribution of sample means is normally distributed, and we are also going to compare it with the original population distribution. Okay, so let's do that. Let's take the sample mean of all the samples we have taken. Okay, so move to the end of all these samples, and I'm gonna name this this column CZ as sample mean. Okay, sample mean. Okay, and we know the formula for sample mean mean is simple average and parentheses. Now all the values are horizontally entered. So I'm just gonna click the first value and press and hold shift button and press the last value here, and then parentheses close. So I have selected the cell D2 to cell CY2 and enter. So the first sample that we randomly selected had a sample mean of 85.37. Now I'm gonna just double click on the fill handle and check all the way down that all the values have, all the samples have their mean calculated. Okay, so this central limit theorem, it states that the distribution of the sample means from a large number of independent, identically distributed sample approaches normal distribution, regardless of the original population. So let's see if it is normally distributed or not. Okay, so first let's see the original population. Is this normally distributed or not? Okay, insert, and let's draw the histograms. Okay, well, I would say not really. It does show some normal distribution, but strictly speaking, there are quite haphazard, and then we see a lot of extreme values on the right. So quite, I would say, digressing from the normal distribution. But let's see if the sample means follow the normal distribution or not. I'm not going to select it by clicking on top, because it's going to select all the values up to 5,000. Many of them are empty, so I'm going to just click on the first value, press and hold shift button, and scroll all the way down to the 1,000th value, which is here, and keep holding shift button and then click on the last value. That will select all the values. Now if I draw a histogram, I see that it is almost perfectly normally distributed. I'm going to put it next to the histogram of the original population. Okay, it is giving me some tough time, which is fine. Okay. Please bear with me. Okay, let me cut and paste. Easier way. Okay. Okay, so here the histogram on the right is the distribution of the sample means, and on the left is the one of the original population, right? So although we see that even the normal distribution, normal population was kind of normally distributed, but the distribution of the sample mean is perfectly normally distributed. Let me demonstrate it with another another value, the smoking status, the smoking values. We know that this is not at all normally distributed. Control C, and I'm gonna replace column A with smoking status. Okay, now you see that the original population is not at all normally distributed. It's just all the values are concentrated on the left, but the sample mean is perfectly normally distributed, right? We can replace, we can test it with some other values, maybe weight, and I will replace it here. Okay, oh wow, okay, so you see this is again normally distributed. Okay, and let's try with one more. I'm not gonna use age at death because there's so many missing values there, so I'm just gonna use maybe height, or maybe age at start. Okay, again we see that the normal population was not at all normally distributed, but the sample mean is almost normally distributed. So that is kind of the confirmation of central limit theorem.